Look up when the sky is clear at night. You'll see thousands of tiny bright dots there. It may seem like they're fixed in one spot, but in reality, they're constantly moving. In 100,000 years, there won't be a constellation with the same shape or pattern we know today. And think about all those red dwarfs, small stars, planets, space bodies we can't see with the unaided eye. Red dwarf stars are especially cool. They're usually about half the size of our sun, and mostly 1/10 as bright. They may not be the brightest things in the sky, but they live for a very, very long time. Nuclear fusion reactions happen deep in star cores. That's what makes them shine. Large stars release huge amounts of energy, burning their stellar fuel. But such stars tend to burn all their fuel in only a couple of million years. Stars like our sun usually live for about 10 billion years, but red dwarfs don't use that much of their fuel. Their light is not so powerful, and they don't require much energy to support their existence. They're like energy-efficient cars. That's why they can last hundreds of billions of years. Some of the smallest ones may live for up to 10 trillion years. Most hydrogen in sun-like stars remains unspent. There's more of this gas in the atmosphere rather than in the core of such stars. This means most hydrogen doesn't take part in the fusion reactions. But it's different with red dwarfs. They circulate plasma throughout their entire bodies. These stars pull fresh hydrogen reserves from their outer layers into their core. That's what keeps fusion reactions running. One day, in the distant future, stars like our sun will run out of fuel and shut down. The universe will be full of small red dwarfs. They won't have enough energy to shine and brighten the space around them. Our descendants, if there are any, will inherit a dim, dark cosmos. As it gets older, the sun will balloon to a size where it will destroy nearby planets. First Mercury, then Venus, and then us. On the other hand, Earth will probably survive, but barely and not for long. The sun will burn it to a crisp when it gets closer. The outer planets of our solar system will also survive, but they'll move even farther away into space. The sun will lose some of its mass while increasing in size. Its gravitational pull establishes the orbits of the planets. When our star becomes less massive, the pull of its gravity will become weaker, and the outer planets won't have such a strong connection with the sun. Our solar system is not isolated. There are many other stars in our galaxy. Within 30 billion years, stars that travel nearby will mess with our outer planets, enough to rapidly launch some of the biggest ones out of the solar system altogether. The last planet to stay will stick around for a while longer, maybe even 100 billion years. But even that one will eventually end up kicked out of the solar system. There's a theory claiming that we got most of the water on our planet from ice-laden meteorites and comets, frozen balls of ice and dust. As they crashed into the early Earth, they probably brought water, which was necessary to develop life. But those very same objects that might have created life on our planet could also be its end. This is not a matter of if, more a matter of when. And scientists think it's very likely that an asteroid or comet big enough to wipe out life on Earth will smash into our planet. But it'll happen in the distant future. And fortunately, we have the technology to predict such things and react on time. But there are other cosmic collisions we can't avoid, no matter what we do. Andromeda, our neighboring galaxy, is moving toward the solar system at a speed of 68 miles per second. There are 2.5 million light-years between the Milky Way and Andromeda, so luckily our neighbor won't cover that distance anytime soon. It'll only happen in around 4 billion years. Such a collision of two galaxies might lead to real chaos for our descendants, if any of them are still living on Earth, that is. The two galaxies will slide past each other. Then they'll draw apart until the gravitational force starts pulling them back together. As they merge, they'll both lose their disk-like structure and form one big elliptical galaxy. It's already got the nickname Milkomeda. The Milky Way as we know it today won't exist anymore. Space is in constant motion, changing all the time. Scientists have a couple of possible scenarios of what might happen with the universe in the future. Number 1, the Big Rip. This theory claims that the universe will expand infinitely. At one point, the pull of the expansion will get stronger than the gravitational force keeping it all together. If this happens, it will tear apart galaxies, stars, black holes, and all other space bodies, including Earth. the universe will turn into a bunch of disconnected particles. Until about 5 billion years ago, the universe was expanding slowly because of its powerful gravitational pull. Then its growth sped up. Some experts say it happened because of the effects of dark energy. Dark energy is a mysterious force that makes up almost 70% of our universe. This force pushes it to expand faster rather than slowing it down. So, in the case of the Big Rip scenario, dark energy will win over gravity to the point where it will be able to rip apart individual atoms. Scenario number 2, the Big Crunch. There's a possibility the universe will get to the point where it'll stop expanding. Gravity will become a dominant force. It might even reverse the expansion of the universe. Then, the cosmos will start shrinking, making planets, stars, and even entire galaxies collide. In the end, the whole universe will collapse in on itself. Once everything compresses into one infinitely small point, which is something called the Big Crunch, the universe may start expanding once again. Theory number 3, the Big Freeze. Brrr. In this scenario, entropy will grow until it reaches its maximum value. Entropy is basically the idea that everything in the universe declines into disorder at some point. Once entropy gets to its maximum, the heat in the system will be spread evenly. The universe will then disappear because there won't be any room for heat to exist. Any mechanical motion inside the universe will stop. The cosmos will be so empty and gas will be so thin that no new stars will be able to form or shine again. In such a cosmos, time is just an endless void. Nothing ever happens with planets, stars, or living beings. The entire universe is frozen, dark, and motionless because there's no energy that can make things start working again. Many, many billions of years after the last stars burn out and fade, black holes will send a message that the universe has come to an end. Black holes are areas with extremely strong gravitational pull, so powerful that nothing can escape it. They can be as massive as 100 suns. As for supermassive black holes, their mass can be greater than that of 1 billion suns. You can find such giant black holes at the center of most galaxies. Like everything else, black holes will experience the same end. But when their moment comes, they won't gently disappear into the night. Black holes will go away in enormous bursts of fireworks, lighting up the universe in the last moments of their existence. It will be the end of the entire era. Black holes usually survive by gobbling down the stars and gas that come close enough. Their gluttony is the main feature that gives them away. In most cases, there's an accretion disk around a black hole. That disk is made of all those materials and particles it's torn apart and is pulling inside, similar to when water swirls down a drain. As the materials and particles draw closer, they start to move faster and faster. This generates heat, which makes the accretion disk glow, which again gives away the black hole. Yep, black holes aren't that great at hide and seek. Things that cross a black hole's event horizon, which is also called the point of no return, are lost forever. But Stephen Hawking had a theory that you might be able to escape from a black hole. There are particles moving even in a vacuum. Let's say one particle has positive and one has negative energy. If they both come close to a black hole, there's a chance that one will fall into it while the other will escape. That means the black hole has radiated the particle away. And this particle has taken some of the black hole's mass with it, which is why the black hole may start shrinking. As it begins to evaporate, it loses its mass and slowly becomes smaller. More and more particles start leaving until all the energy that's left behind escapes all at once. In the final tenth of a second, there will be a giant flash of energy and light in a very, very small region of space. And then, it's all gone.
We travel back in time to 4.6 billion years ago to see the moment when our solar system was born. Wow, there's nothing that looks like a star or a planet. So far, there's just a giant cloud of dust. It's called a nebula. These are molecules of hydrogen in heavier elements, along with ice, left there from a previous star. But this cloud isn't dense, so it can't turn into a star or a planet. But then a blast wave comes here, maybe even several. There's a supernova explosion a couple of light years away from our nebula. This is when a giant star burns off its fuel, then collapses under its own weight. At this point, a boom of such force that its light can be seen dozens of light years away. The blast wave from a supernova reaches our nebula. Like a sea wave, it hits the dust cloud, causing it to shrink and become denser. Then the nebula gained a common center of gravity. It attracted more and more dust particles to itself. This put a lot of pressure on the nebula's core. It started spinning. And the greater the mass of the central cloud, the faster it rotated. The particles inside the core collided faster and more frequently. This raised the temperature of the nebula to several thousand degrees. At this point, a protostar appeared. It was a young and unstable sun. When the temperature in the nebula's core reached millions of degrees, nuclear reactions began there. The cores of light elements like hydrogen and helium hit each other and fused into heavier elements. Let there be light. 4.5 billion years ago, the protostar evolved into a stable sun, but 30% dimmer than we have it now. There's also a giant cloud of dust left behind. This is the remnant of material that didn't take part in the creation of our star. Now you can see the larger objects in this cloud. Heavy elements and dust began to pile up, forming protoplanets. At this stage of our solar system's existence, there were about 100 protoplanets, ranging in size from lunar to Martian. Back then, there was nothing but total chaos. These protoplanets didn't have clear orbits, and they began to collide with each other. Some crashed into a pile of debris, creating massive explosions. Others collided tangentially and simply changed their trajectory. In this cosmic billiards game, the largest protoplanets won. They literally ate the smaller debris and got bigger and bigger. The chaos didn't stop until about 100 million years later. You can see some nearly formed planets: Mercury, Venus, Earth, and Mars. Our home planet now looks more like a lump of lava. The constant bombardment of the surface by various asteroids has heated the planet greatly, but now it has begun to cool down. Everything went quite well until an unknown villain appeared on the horizon. It's Theia. It's a hypothetical planet the size of Mars, formed around the same time as the other planets. And now, it's spiraling toward Earth, ready to hit it. Bam! As a result of the impact, a huge chunk of our planet was knocked out into space. Theia herself was blown to pieces. Its core merged with the core of the Earth, while the rest of the material remained in our planet's orbit. Gradually, the debris from both planets began to collide with each other and merge into a large cosmic body. When the dust settled, the Earth received its satellite, the Moon. Another hypothesis for the formation of the Moon suggests that Theia was much larger than Earth. It only lightly scratched our planet and continued moving without losing its material. And the Moon was formed almost entirely from particles of our planet. As proof of this hypothesis, we have samples of lunar soil delivered by the astronauts of the Apollo mission. It turns out that the lunar soil is very similar in composition to Earth's crust, and it could only have gotten there as a result of some violent event. Gas giants like Jupiter, Saturn, Uranus, and Neptune formed a little later and further from the Sun. These planets are literally balls of gas. There's no solid surface. If you step on Jupiter, you'll fall until you reach its core. These guys couldn't get a solid surface for several reasons. They formed later when other planets took over the metals and silicates. They also all originated beyond the frost line. This is a hypothetical point somewhere beyond the orbit of Mars. The sun doesn't heat the area behind this line enough for water to be in a liquid state. So there was a tremendous amount of ice in the remaining clouds of gas. 3 million years after the birth of the sun, these building materials started to pile up and build mass, becoming Proto-Jupiter. Within a couple of million years, this ball of ice could reach a mass about 50 times larger than Earth. And the heavier it got, the more gas from the disk it was able to accumulate. In a short period of time, Jupiter absorbed almost all the material from the disk of gas near it and accumulated about 318 Earth masses. Jupiter had a very strong gravitational field, and it wreaked havoc on all objects in the area between Mars and Jupiter. Protoplanets collided there much more often, causing them to collapse. As a result, we have the asteroid belt. These are fragments unable to reassemble into a full planet because of the intense gravity of the gas giant. Saturn, the next of the 4 gas giants. It's 3 times smaller than Jupiter. It's thought to be so small because it's even farther from the Sun, about 10 Earth-Sun distances. And it began its formation even later when Jupiter left almost nothing of the gas disk. But Saturn got another distinguishing feature: the rings. They're so wide that you could fit 21 Earth planets on them, and they're as thick as a 5-story building. We still don't know how they were formed, but there's 2 main hypotheses. So Saturn has 82 moons discovered so far. There may have been one more, but it was destroyed in a wild collision. The moon was shattered into small fragments that began to orbit the gas giant. These fragments, in turn, collided with each other and shattered again. Gradually, debris the size of a skyscraper turned into small grains of sand. Yep, Saturn's rings are made up of cosmic dust and ice. Then come Uranus and Neptune. They are much smaller, only 14 and 17 Earth masses. It is believed that they couldn't reach the size and weight of Jupiter because of the strong solar wind. It gradually blew the gas disk outside the solar system into interstellar space. So there were much fewer building materials for new planets. When Uranus was formed, it experienced a catastrophic collision with another protoplanet, and probably a very large one. The collision caused Uranus to fall on its side. All planets have their axis of rotation pointing upward, but the axis of Uranus is pointing toward the Sun, so it looks more like a rolling ball. Only it's rotating retrograde. That means it's spinning against its own motion. It's like a car driving forward, but its wheels spinning counterclockwise. Behind the gas giants is the Kuiper Belt. This is the area beyond the orbit of Neptune. This is where the asteroids, dust, and ice were left after the solar system formation. It's similar to the asteroid belt between Mars and Jupiter, but it's about 100 times heavier. Knowing how our solar system was formed, let's see how it might be destroyed. The Sun has a lifespan, just like any other star. Right now, it's about halfway through its life cycle. Every second, the Sun turns 4 million tons of matter into solar radiation. Gradually, it'll run out of fuel and begin to burn heavier elements within it. This will increase the temperature, luminosity, and size of the star. In 1.1 billion years, the Sun will be 11% brighter than it is now. The seas and oceans on Earth will begin to evaporate, and our planet will heat up more and more. In 3.5 billion years, its brightness will be 40% higher than it is now. Conditions on Earth at that point will be similar to what we have on Venus now. Life will be simply impossible. In 7.8 billion years, the Sun will start burning hydrogen in its shell. This will cause it to expand and become a red giant. It'll be about 256 times larger. At that point, the star's outer shell will be exactly where the Earth's orbit is now, but it'll lose its mass. So there's a possibility that our planet will migrate a little further away from it. But it won't matter, because life on Earth won't be able to exist for several billion years already because of the high temperature, and a strong solar wind will simply blow our atmosphere away. Then the thermal pulsations inside the star will tear off the outer shell of the Sun. This shell will turn into a planetary nebula, almost exactly like what we saw at the beginning. And all that will be left of the Sun is a white dwarf, the size of the Earth, which will fade away for a few billion years.
Black holes tearing apart enormous stars, pulsars spinning at incredible speeds and emitting powerful beams of energy, colorful nebulae with fireworks of newborn stars, galaxies of every possible color and size. All of these are found within our universe, but it's not infinite. It has a boundary, a literal wall, and beyond that, there's an absolute nothingness. Right now, we're going to make a journey to that wall. But first things first, our universe is like a humongous nesting doll. If you open it up, there's a smaller one inside. It's a galaxy. Inside that is an even smaller doll. That's our solar system. And the smallest doll of all is the Earth. Each of these dolls has boundaries that we're going to cross. For that, we'll need a spaceship, and a big one. It also has to be able to move 100 times faster than the speed of light. You get on board and start the engines. 62 miles above sea level is our first boundary. That's 10 times higher than passenger planes fly. This point is called the Kármán line. It separates the atmosphere of the Earth from outer space. Now we fly further, to the edge of our solar system. We turn on the hyperdrives and fly past Mars, Jupiter, Saturn, Uranus, and Neptune. We've traveled a distance of 100 astronomical units. 1 AU is the distance from Earth to the Sun. And here's the boundary of our solar system, the heliosphere. Here, the speed of the solar wind decreases rapidly. First, it drops from 620,000 miles per hour to the speed of sound. Then, there's a layer called the heliopause. This is where the wind almost vanishes. And then, our ship experiences a bow wave. This is where we feel the force of the interstellar wind, which collides with the boundary of our solar system. When you pass this boundary, you find yourself in the dark of interstellar space. And here, you can find 2 human-made objects that made this trip for the first time in history. They're Voyager 1 and Voyager 2. Voyager 1 crossed that boundary in 2004. Voyager 2 did it in 2007. These space probes discovered that the heliosphere is not a perfect ball around the Sun. Its southern boundary is 10 AUs closer to the star than the northern one. So, we're moving in interstellar space and will soon approach a stone wall around our solar system. 200,000 AUs further, and there it is. This wall of rock is the Oort cloud. In fact, it's a pile of asteroids that surround our world. Scientists speculate that the Oort cloud could be the source of comets and meteorites that fall to Earth, but they're so sparse that we easily fly between them. Now we're in complete darkness. The Milky Way is about 106,000 light-years wide. In a conventional rocket, it would take billions of years to fly across that distance. But you throttle to the max. You masterfully fly past the stars and planets as if on a racetrack. And within minutes, you're at the edge of our galaxy. There's no more interstellar wind. All you see are bright dots somewhere in the distance. These dots are huge galaxies. We need to look at a map to make a route to the edge of our entire universe. You're here, near the Milky Way galaxy. It's part of a cluster of galaxies called the Laniakea supercluster. But even this huge thing is like a little street in a big city. Zooming out, we find Hydra Centaurus supercluster. Thousands of galaxies on the map look like little dots. Maximum zoom out. This is our entire observable universe. We thought it was infinite, but we may have proof that it has a boundary. It's here, 10 billion light-years away from our home. Even if you travel at the speed of light, a trip there would take twice as long as our whole planet has existed. During that time, the sun will either fade away or explode like a supernova, destroying our entire solar system. And if you can live that long and then return home, you will see that our galaxy is there no more. It's long since collided with the Andromeda galaxy and merged into one big cosmic body. Luckily, your ship is able to warp space-time so that this journey will literally take a few seconds. Boom! Congratulations! You've arrived at your destination, the Eridanus supervoid. Some scientists believe this location is the evidence of collisions of our universe with something big enough to leave such a large scar. The Eridanus supervoid is an empty and cold space 1 billion light-years wide. If you think of this void as a cup, it would fit at least 10,000 galaxies, and it appeared after an accident of gigantic proportions. The object that crashed into our universe was another universe. Yes, other universes may actually exist. Imagine that our entire universe is a huge bubble that contains all the clusters of galaxies in the observable universe. There could be an infinite number of such bubbles. They could have been born during the Big Bang. These universes may be different from ours. They may have other galaxies and nebulae. But these bubbles could also be parallel universes. This means that if you chose cereal over oatmeal in the morning, in another universe, your twin would choose the oatmeal. Every choice you ever made in life had completely different consequences in a parallel universe. And because the number of choices are infinite, there's a whole infinity of parallel universes. So, like a regular bubble, our universe has a wall that is near the Eridanus supervoid. Long ago, another bubble flew past ours. As they approached each other, their gravitational fields began to interact. Our boundary wall began to deform and pull toward the other universe. The same thing happened on the other side. Then the walls of our universes came into contact. But as these bubbles moved, their connection began to break, and the other universe just ripped a huge chunk of ours. A cold void was formed at the point of collision, and that was the Eridanus supervoid. The problem is that the universe looks the same to the observer, regardless of point of view. For example, imagine a basketball hanging in the air. Now, if we put an ant on the ball and tell it to find the edge of the ball, it will start running around it, making an infinite number of circles. But the landscape around the ant will not change. All it will see is a rounded horizon. That's because the ball remains the same from any point of view. The same thing happens to us when we try to find the edge of our universe, all because we imagine the world in three-dimensional space, and our view is limited. For example, you see an ordinary square in two-dimensional space, but if you add depth and change the point of view, voila, it's a cube. If we could see the universe in four-dimensional space, a square might be something completely different. But maybe we can leave our home bubble. The key to traveling to another universe might be inside a black hole. A black hole is one of the most mysterious objects in the universe. They're so heavy, they warp not only space, but time as well. It's like putting a heavy boulder on a net. The net will sag, and the closer you get to the boulder, the stronger the curvature is. Once you're in the gravitational field of a black hole, you can't leave it. We still don't know what might actually be in the heart of a black hole. Some scientists speculate that white holes also exist. Theoretically, they should be born along with black holes. Except for the color, they're the exact opposite of black holes. Nothing can come close to a white hole. At the moment, there's no data on such objects, but general relativity theory suggests they do exist. There's also a theory that a black hole may be a passage to another universe. When you get into a black hole, you can come out the other side through the event horizon of the white hole. So you bypass the boundary of the universes and find yourself in a completely different world. But we may have proof that a white hole exists. In 2006, scientists discovered an unusual burst of energy somewhere 1.6 billion light-years away from Earth. This burst was unique. It didn't look like a supernova explosion or even the merger of two black holes. Some astronomers believe it was the birth of a white hole. But because it was unstable, it was destroyed almost immediately. This process was reminiscent of the birth of our entire universe, the Big Bang. So, scientists called it the Little Bang.